Okay, well, thanks everybody for hanging in there. So this will be an overview of how AGWA has been used for post-fire watershed assessment. And we've got a few premises just on some of the analysis we've done that changes in roughness can explain much of the post-fire hydrologic and response and erosion response in non-hydrophobic soils. I think we've proven that AGWA provides a framework to quickly parameterize watershed models and visualize the results. You've seen a number of examples of that. And AGWA provides water scale assessments for both runoff and erosion, sediment transport at multiple points of potential risk and for all model elements, including those downstream of burned areas. And how did we get started? In 2011, the then largest wildfire in Arizona, the Wallow Fire, AGWA was the only method that produced results for the entire burned area. And between 2012 and 2015, it was used in over 21 large fires. We're up to about 55 now and almost 5 million acres. And actually one of Dr. Gurton's former students, who's a BAER team leader for BLM, called him on the way down to the Wallow Fire, and we got talking, and Shay, working very, very hard and very diligently, was able to accomplish this post-fire watershed assessment. And that was over this huge region that I think had 5 BAER teams in it. So it's been formally adopted by the Department of Interior National BAER teams. And in terms of model parameterization for post-fire, we define lookup tables, again, with the infiltration and roughness parameters for pre and post-fire model parameters as a function of land cover, burn severity from gauged basins in which there was pre-fire data, both rainfall and runoff available, and post-fire watersheds, again, with good rainfall and runoff data. So in SWOT, we're altering the curve number and roughness. And in Kinneros, we're altering the roughness, interception, the canopy cover, and the hydraulic conductivity. And based on discussions with Pete Robichaud, who's a fire researcher for the Forest Service, the following reductions were assumed based on a function of burn severity. So for low severity, we're assuming the cover is decreased 15%, moderate severity 32%, and then 50% for high severity. And in Kinneros 2, a cover reduction also decreases infiltration rates. And again, for K2, we set up a roughness factor for overland flow to basically equate to bare soil. So we're notching the Manning's roughness value down a great deal to 0.011. And that's typically more than an order of magnitude change than for a extremely rough environment that may have a lot of litter, needles, down sticks, vegetation, and that sort of thing. So here's a typical AGWA application for the DOI BAER teams. And we set up a cooperative agreement, interagency agreement with DOI. So a number of the folks on the AGWA team deployed on actual wildfires. And then we worked over time to put in capabilities into AGWA that would help them, the BAER teams, speed up their processes, create output that they could put directly into the BAER reports they have to do. And for those not familiar with BAER, it's a time-sensitive process. They have to go in and assess the fire and create a report to apply for emergency mitigation dollars, and all that has to be done in about 14 days. So this point in time, they know or get warning when the fire is about 80% contained that they will be deploying to a fire, and then they'll actually start to mobilize at around 95% containment. So even prior to deploying, they can talk to local emergency management folks and land managers to identify values at risk. So values at risk may be a campground, an archaeology site, a road crossing, culverts, things that might be affected by high runoff impacts after a fire. So you can then include a point shape file for all of these values at risk. So over on the right, you see a number of places where values at risk, where you want to make sure that the discretization of AGWA produces runoff at that point. So AGWA will automatically force a channel break at that point. And so you can identify as many of these as you want to make sure you're looking at that value of risk with the model outputs that are computed at that same location. Let's see, how do I get rid of this? There we go. And they can import the bark map. So they can do this in a two-step process now, because AGWA has given them a lot more ability to speed this up. So the bark, or the burn area reflectance map, that's produced by either USGS or Forest Service, is produced via remote sensing methods, and they can use that stratification and run the bark map compared to the pre-fire conditions, and actually help them stratify their work procedures and work locations to help produce the field verified burn severity map. So they get the bark map, a lot of crews go out into the field to certain areas. They do on-site verification of the burn severities to create a final soil burn severity map. And then you would go through the process again, simulate post-fire with the burn severity map, difference the pre and the post-fire simulations. And again, this allows them to target mitigation efforts and apply those methods where they're going to be most used, or the best, highest values. And we did a demonstration on the Elk Fire Complex, I think that was 2013 in Idaho, where this could save up to $7 to $8 million, because their default position is that they will try to mitigate moderate and high burn severity areas. So that's just kind of the process that the BAER teams run through. And here are some of the results that we can see. So this is an example of the Las Conchas fire on the Frijoles watershed in the Bandelier National Monument. So you can see the Las Conchas fire that burned the headwaters of a whole bunch of these watersheds. Here's the Frijoles, and the Bandelier National Monument Visitor Center is right down at the bottom of this. And you can see this middle portion of the watershed was really burned badly. And a number of us visited the watershed site at the next year's pre-fire BAER meeting. And this was a really hot fire that just cooked the soils. There was very little regrowth. So AGWA discretized the watershed and applied rainfall to the crosshatched area. And we'll talk about, how you would want to apply rainfall further on in this presentation. But again, we see the watershed peak coming out of the highest or the darkest events here, And, pretty large flow in these two channels, but in the final channel segment, it's calmed down, or it's diluted, I guess, from the unburned areas. And so, here's some of the stats and the percent change for, excuse me, peak flow, peak sediment, and sediment yield. And again, these numbers are from the estimates that we did. They did not have gauge data, excuse me, either rainfall or runoff. And so these are the sorts of graphs that the BAER teams like. So again, post-fire in red, pre-fire in black. And this is driven by a 25-year, 6-hour storm. And again, this is a quantitative and I'd say highly uncertain estimate. And the BAER teams have even said now that they prefer to show percent change, because when they put numbers up like this, someone will invariably ask, how did you get 9,000 for a peak post-fire flow rate when you don't have any gauge data? So this is an independent study, little overview that was done by some folks at the Desert Research Institute. So they gathered some pre and post fire data from the Sandimas Experimental Forest. And they used these 4 methods. So there's a kind of a rule of thumb method, which is largely based on experience from those who have worked in the forest, a modified rational method, or MODRAT, an HMS HEC model using curve numbers, and Kinneros. And again, that was published in 2013, and that reference is on the AGWA website. And here's what their findings were, is that the rule of thumb and the modified rational method were okay with careful local calibration. In other words, you had people that had good experience with runoff on these watersheds who could tweak the model to get it in the ballpark. The HEC model with curve numbers performed better for the pre-fire prediction, but Kinneros did better for the post-fire prediction. And they attribute this to that pre-fire is typically a saturation excess runoff production, or more subsurface, than post-fire infiltration, which is typically more infiltration excess. And Kinneros right now in AGWA only does infiltration excess with a single soil layer, but as we saw in that earlier presentation, it can do saturation excess from shallow soils over rock with the 2-layer infiltration approach. So again, some basics on runoff generation. Often in steep mountainous terrain, you may have bedrock, fractured rock of a mountain over, in some cases, relatively shallow soil depths. And when the water infiltrates, it will hit the bedrock and often come out laterally. And so it's got a lot of travel distance through this porous soil surface. So it has a slow response, and the peaks coming out of it are attenuated a great deal. So, this is what this article by Chen was saying, that this is more typical in unburned areas, with shallow soils. And for infiltration excess, the rainfall intensity has to be greater than the soil infiltration rate. And again, this is more typical in burned areas under storms with high rainfall intensities. And again, the saturation excess is, you have wet areas, you have a shallower water table, and basically, even though the rainfall may be coming down more slowly, It doesn't have as much pore space to infiltrate into, so it will eventually fill up and overspill. And again, they're saying that the curve number seems to represent this process better, and that Kinross Agua uses infiltration excess and does better for the post-fire simulations. Now, how did we come up with this idea that the real key, at least with the data that we've analyzed, is that we don't so much change the infiltration a great deal, but we really crank down the hydraulic roughness. So this is, again, some actual data pre and post fire on the Aspen fire. Marshall Gulch is a small watershed originating almost at the top of the Catalina Mountains, just north of Tucson. So this is some data for a storm in 1957 and a post-storm. So the fire was June 17th to July 10th in 2003. And this storm occurred just 2 weeks later. And although they're not exactly the same storms in terms of total depth and whatnot, they have a lot of similarity. So in the pre-fire storm, we've got an average storm depth of 54 millimeters. Post-fire, in this particular fire, 43. The runoff volume is about 10 millimeters here, about half that post-fire. The runoff to rainfall ratio, 0.19 in the pre-fire case, 0.11 post-fire. And again, notice the difference in the peak rates and the differences in the scale on the left-hand side of the y-axis. So post runoff rate, this is millimeters per hour over the watershed area, 0.16. And it's almost, well, it's 30, roughly 30 times as much on the post-fire case. So the big characteristics we see are both huge increase in post-fire flow and the peak rate, and then a great difference in post-fire, pre and post-fire timing. So this hydrograph, the biggest part of the hydrograph is taking about 3 to 4 days, and then you still get runoff out in the tail up to 10 days. In the post-fire hydrograph, you can see virtually the whole storm hydrograph is done in about 3.5 hours. So response time changes greatly, peak rate changes greatly. And this sort of an effect of shortening of the timing and increase in peak rate can be adjusted by using a lower roughness number. So, in a curve number treatment, to mimic a high increase in peak flow, they have to knock down the curve number. But what that does, though, is also increases the amount of runoff volume to amounts that really aren't realistic in observed data. And this has been observed in a number of studies. So next question. Now we're in a place, there was a fire. Again, there's no rainfall information. And we typically default, and the BAER teams do this too, to design storms. And the typical goals when you're modeling post-fire runoff, you'd like to accurately predict or reproduce the magnitude of the peak flow, and also predict which stream reaches and hill slopes are at high risk for either high runoff flooding or erosion. And Gabe Sidman, one of our graduate students, investigated this in terms of what's the best way to represent the rainfall when you have no historical data. And he looked at 2 fires, one in Zion National Park, occurred on August 1, 2007. And this event was a little over a year after the fire. And I can see the fire didn't burn a high percentage of the watershed. And then On the other side, the same fire we looked at before in the Frijoles Canyon in Bandelier. And so the advantage of this is that we did have radar rainfall estimates for the actual storms that are listed here. And again, you can see the colors represent different burn severities, with red as the highest. So what rainfall representation gives you the best estimate of peak recharge? So from a design storm case, so let's take, again, the NOAA 14 estimates are for, let's say, a 20-year return period, and you select a duration, and let's say there's, again, 2.28 inches of rain that's associated with a 25-year, 6-hour return period storm. Well, you could apply that intensity uniformly over the watershed. And as Shay showed earlier, you could use a type 2 storm type to put it over the whole watershed, or a type 2 over the burned area only. And the green trace is the actual radar rainfall data. And, you know, so as you can see, these hyedographs look a lot different than the actual rainfall hydograph is derived from radar. And, you know, radar is not perfect either, but it's a lot different in these design storms. So when you apply it uniformly, either over the watershed or only over the total watershed, either type 2 or uniform, you're putting a lot more water onto the basin than is typically realistic, at least in a thunderstorm environment. The storms don't dump that much rain uniformly over the whole watershed. So using these inputs then, what do the model outputs look like? So here's the radar representation for the Zion Park event, and we can see you know, some relatively high burn severities here, and relatively high rainfall rates. So the red corresponds to the red over here. So the total rainfall depth, you know, is up over 3 inches, 75 to 82 millimeters. So approximate duration of the event, 1.5 hours. And if you go back to the NOAA 14 tables, this correlates pretty closely to a 10-year rainfall event. And here are the differences you get in peak discharge and time to peak for those different representations. And down here, we have an estimate from indirect gauging methods of what the actual peak runoff estimate would be and time to peak. So, you know, as expected, the uniform rate results in a very low intensity, so it doesn't produce any runoff. The type 2, you know, starts to produce some more, and if we just do type 2 over the burned area, starting to creep up, and then the radar data actually gives us a peak that almost is within the uncertainty band of the indirect measurements. And then similarly for Frijoles Canyon, the observed estimated indirect peak rate is just about 200. And the radar is almost right on with that. And again, within the uncertainty bounds of the peak rate. So, you know, if you've got radar rainfall data, that's great. If you don't have any data, you're going to apply it in one of these fashions, and you're deviating from observed quite a bit. So again, there's the radar, pretty good estimate. So then the next question to ask is, well, does the rainfall representation change the model's prediction of high-risk areas? Again, for rapid assessments, you typically want to use a design storm. And for monsoon events, that may be the 2-year, 30-year duration event. In this case, in that area, that's going to produce about a 1/2 inch of rainfall. So, which hill slopes and stream ridges have the greatest change in runoff or sediment yield from pre to post? So remember, the fires concentrated down in this part of the watershed, and this is applying the SCS type 2 storm over the burned areas only. And again, the darker the elements in brown, the higher the percent change in sediment. And for the channels, the darker blue and thicker line, highest percentage change in peak flow. So now let's do this exercise with putting these 4 different types of rainfall distributions over this area. And does the rank ordering of highest to lowest, is it maintained by doing these 4 types? In other words, are we going to get the same risk ordering from highest to lowest for these different types of rainfall distribution? Again, we're in an area let's assume it doesn't have radar and it doesn't have particular rain gauges. So what we're going to do is, again, see if the modeled areas of at-risk areas will be maintained from a pre to post-fire rainfall and how that might change with representation. So again, going to model North Creek with all 4 cases. We're going to model Frijoles with all of those. And here's the inverse rank zone. So this is from lowest to highest. And again, from the lowest to highest, indicated by the colors and the thickness of the channel lines. And you can statistically compare the rankings with a Spearman's coefficient. So if the Spearman's coefficient is 1, it implies there's perfect agreement in the rank order. And if that coefficient is -1, it implies a completely inverse ranking order. So highest on one, lowest to the other, and down the line. So here's the comparisons on North Creek. So in blue, you're looking at the Spearman coefficient here. This is the type 2 and the burned area only. Type 2 in the whole watershed, uniform, and then with the monsoon design storm. And so these values are quite high. Again, they're getting close to 1 on all 3 of the lower events. So again, the brown or the lower side of the matrix is for the Spearman ranking for sediment yields. And again, so you're ranking all of the hill slopes and comparing them from the different rainfall representations. Up in terms of peak flow, that's the blue side, the statistics aren't quite as strong, but again, they're well over 0.5, except in this case. And now here for Frijoles Canyon, you get much better statistics in the peak rate, and again, quite high statistics in the sediment yield. So, the point is, these are generally, the rankings are generally, pretty much the same. There may be some out of order in a few of the elements, but the conclusion is that the rainfall representation, again, will change, as we saw with the radar, our ability to accurately model post-storm fires. And, if you've got it, the radar is the best way and you should use it. But the high risk areas don't vary drastically between the rainfall representations. So we feel AGWA Kinross 2 can reliably be used to predict post-fire relative change, pre to post-fire, to identify these areas. And the best one that you saw there was that, if you looked at the matrix carefully, was applying that design storm only to the burned area, not the whole watershed. So I think that's all. Let's see, again, the point being that the models are more reliable at predicting relative change than absolute change. And so we've even had discussions with the BAER folks that, you know, maybe, and Weather Service works on these too, that maybe in talking to the local folks, and they say, you know, there was a really big flood in 2016 in June, that maybe you should go back and get the radar data associated with that big storm that caused flooding and apply that pre and post storm. And that would be potentially a more realistic check on trying to look at pre and post fire change. And I think, oh no. So what did we learn? A design storm with precipitation uniformly distributed over the area can accurately identify the ranking pre and post, but the best way is to do it on the storm or the burned area only. But the whole BAER team benefited from the initial results. And again, this is helping them figure out what's the best way to go from a bark map to a field verified burn severity map. And again, the differences were used by the BAER team to help locate where they should put their treatments, you know, highest value. And, you know, they have a matrix in terms of risk. And of course, you know, saving lives is the highest value. And then, you know, they prioritize what they'll protect depending on the risk and the values associated with that risk. And, you know, this has helped other agencies in terms of the Corps engineers, statewide hazardous planning groups, identify site-specific modeling needs and design emergency warning systems. So again, we're coming into a bad Western, you know, fire season again. We had virtually no winter rains in the Southwest. In my yard, the weeds aren't even growing. So it could be another really bad fire season. And again, we've been fortunate enough to work closely with the BAER teams, and this has been a useful tool for them. And that's it.